I will talk to you today about thin film materials and their deposition methods, basically for building microsystems that we have seen in the previous lectures. As we have seen in the previous lecture, one of the key steps in the whole chain of events that are required for fabricating microsystems is essentially deposition. This is done by various methods, and various different materials can be fabricated by the methods that you will see in today's lecture. Thin films are essentially thinner versions of the common engineering materials that we use in various fields, and they have in their bulk they have properties such as electrical resistivity, optical characteristics, and various other parameters that we normally look for. These properties, when they are in bulk, are reasonably fixed and and restricted, whereas when it comes to thin films, we can actually engineer their characteristics to a certain extent by modifying the process by which these are deposited, and this is basically due to the size effect. And when we talk about thin films, essentially these are films of the order of, let us say, hundreds of angstrom thickness, or let us say tens to hundreds of nanometer thickness. Hence, at that thickness level, we are essentially talking about films that are possibly several atoms or molecules thick, and hence the properties are much more predictable and also dependent on how these are assembled. One very common example that can be cited in this context is like how would it look between, let us say, a heap of bricks or an ordered or stacked, properly stacked assembly of bricks. If you really do that one by one, layer by layer, that stack of bricks is much more stronger, and also much more with much more predictable characteristic than a simple heap of bricks that if you just pour it onto a surface. So, and because of that, this layered thin film kind of materials have wide range of applications in IC as well as microsystem processing. Obviously, since these are thin films, the the volume occupied by these, and hence the devices made of these are much small. So, they occupy less space, and the overall requirements in various contexts in terms of materials, in terms of energy required, and etc., would be far less when materials are handled as thin films. So, going back to what was discussed in the previous lecture, various types of thin films are used in the fabrication of MEMS and microsystems. These include semiconductors, various metals, several special materials, and also several dielectric materials, including derivatives of silicon. We also see here polysilicon, and I will discuss what this is a little later in this lecture. One of the easiest film that can be made on a silicon wafer is the outside of silicon, and it can be fabricated in a simple furnace like this by processes known as oxidation, and whether there is steam present or not, we call it wet or dry oxidation method. And the chamber that you see here is a dry oxidation furnace, in which you have these gas outlets, and there is a series of wafers assembled, and all these could be oxidized simultaneously using these heating coils outside the quartz tube where these are arranged, and you have this gas flow here. The wet oxidation process is relatively faster, but the films grown by this are typically less dense and porous, and hence where the requirement is for porous films, one usually goes for wet oxidation and vice versa. So, dry oxidation is a little slower, and and typically denser films can be formed. As you could see, the amount of silicon consumed for the oxidation is typically about 44 to 46% of the thickness of the final oxide that is formed. This can be obtained based on the chemical equation of the formation of the oxide. How do we calculate this? We basically start with the molecular weights of these materials, the ingredients, and so essentially we can say that 28 grams of silicon would result in 60 grams of oxide, and knowing that the densities of silicon and oxide are 2.33 and about 2.24. Again, this could vary, the oxide density could vary based on the approach by which it is fabricated, and based on these we could actually calculate the volume of the silicon consumed to the volume of the oxide that is formed, and these could be worked, and hence we can see that about 0.44 micrometer thickness of silicon would result in a micron thick of oxide. So, this is one good way of calculating the oxidation procedure, the thicknesses of the material that is formed. In fact, the rate of oxidation by either of those processes would depend on various factors. It depends on the crystal structure of the silicon, that is whether it is a 100 wafer or a 111 wafer. In a previous lecture, we have seen that the chemical characteristics of the silicon wafer depends on the crystallinity, and silicon is primarily an anisotropic material. It also, the oxidation rate also depends on the doping and presence of various impurities in the oxidizing gas, and also the other parameters that one can use in the process. Typically, the oxide thickness is measured by an instrument called ellipsometer, and we work with a standard table of colors based on how the wafer would look. You make use that and then determine the thickness. But oxidation is only possible in the case of silicon and only to form silicon dioxide. In general, to work with thin films, we need to start with the source material of the thin film and transport this source material and condense it onto the substrate. So, a series of process steps would be required in a general scenario when one would want to deposit a thin film onto a wafer, whether it is silicon or other materials. And obviously, the nature of the film deposited would depend on various process parameters, including what the substrate is, and the temperature, pressure, whatever gases that you are using, and various other factors similar to that. So, we can create essentially in the deposition process, what we are trying to do is that we create the most favorable process conditions, so that material is transferred from the source to the substrate material, substrate surface in the most efficient manner, and so that we get the best quality films, possibly with the maximum thickness possible within the minimum time, so that we get some kind of a engineering improvement over there. There are basically two approaches. One is called the physical vapor deposition, which is essentially the physical transfer of material from the source, which is normally known as the target, to the substrate. And whereas in the case of chemical process, it's essentially based on the some kind of a chemical reaction to deposit the material onto the target, onto the destination, which is essentially the substrate. Normally in chemical vapor deposition, we will only have reagents coming in, mostly in the gaseous or some kind of precursor form. Major deposition schemes therefore are based on either they are physical vapor deposition or chemical vapor deposition. In some examples of physical vapor deposition include the evaporation technique and what is called the sputtering technique. There are several variants of these, as you will see in subsequent discussion. There is also, as I mentioned, chemical vapor deposition techniques, which is typically used for better quality films. And there are some other methods which are used for specialized purpose. For example, electroplating is used when one needs really thick films of materials, relatively speaking, and spin casting or spin coating methods are used for polymeric materials, including photoresist, which are required for patterning. And there are also epitaxial growth of semiconductors like silicon over a surface and things like that. Let us first look at this example of thermal evaporation, which is usually done within a chamber like this. Let us look at one of the common examples of evaporation that you would have seen in your own house. One of the common examples is basically you would have seen water boiling in a vessel in the kitchen, and if you put a cold lid over the boiling water, you can see that the water condenses in that on that lid surface. Evaporation is essentially the same thing done for engineering materials such as metals, which could be melted at relatively low temperatures. Hence, evaporation technique is usually used for metallic materials, but obviously metals cannot be melted at let us say 100 degrees centigrade or anything near. So, one needs to essentially reduce the pressure within the chamber, so that the melting temperature required for the metal is relatively once again under control, so that it is not too high, and we need to have some kind of an arrangement to create that kind of a temperature. And so, essentially the evaporation rate will therefore be a function of the vapor pressure of the metal that is being deposited. One of the common examples is aluminum. which has a relatively high rate of deposition when deposited by evaporation. And a relatively very good a good quality of film can be obtained at a good thickness by the evaporation process, and it sticks very well with the silicon substrate, and hence you will see that aluminum is used in ICs quite often, and one of the reasons is that it can be deposited relatively easily. The source material will be shaped, whether it is in terms of filaments or springs, or whether it is in terms of small pellets. It all depends on what is the heating arrangement. And one of the simplest way of heating, especially used in the context of, let us say, aluminum, is resistive heating, and is typically used in a lab setup where there is a tungsten board which is heated, and these pieces of aluminum are kept over it, which would melt and evaporate and getting transferred onto the substrate surface. But most materials have much higher temperatures and cannot always be melted just by heating them. So, we use other ways of energizing their atoms or molecules from the source, so that these could be displaced and transported onto the substrate surface. What you see here is an arrangement in which an electron beam is used for evaporating the source materials inside a crucible, and these could be directed towards the wafer in a carousel. It is also possible by RF induction to generate such beams which could essentially displace these atoms from essentially the source material inside the crucible, and these approaches would result in relatively better quality films compared to the simple heating based approaches, and have reasonably good deposition rates. But because these include energy transfer from one beam to another, there could potentially be damages happening in the devices on the substrate, and hence one has to basically choose the kind of approaches that would be required in a particular context. And obviously, the system required for such deposition could be more expensive than the previous. What you see here is an image of an opened out chamber in which this electron beam gun can be seen very clearly. In the second physical method that was listed there is sputtering. So, this is once again a physical phenomenon of transporting, and in this case it is done by creating a plasma, and the ions created by this plasma are directed or attracted towards the positive ions are attracted towards the cathode, and the source material is kept at the cathode, and these ions, when they bombard the target, the atoms from there are sputtered out, and we keep the wafer at the anode, so that the displaced atoms, sputtered atoms that are coming out from the target material will go and attach onto the wafer at the anode. So, the film essentially grows on the wafer. Once again, to create this plasma, one would require a low pressure, and hence this is done in a vacuum enclosure. So, the source material is at the target and in the substrate for sputter deposition is kept at the anode. The so, the target, as I mentioned, is at a high negative potential, and the ions that are there in the plasma, the argon is typically used as it is an inert gas, and these can be used for the displacement, and the displaced atoms, as I said, are condensed onto the wafer. There is a terminology called sputtering yield, which is essentially the average number of atoms ejected from the target, which is kept at the cathode, and that will depend on the incidence angle for the ions, the energy of the ion, the mass of the ion and the target atom, and the surface binding energy of atoms in the target. And hence it would vary depending on the target material, and as you could see from the list below, with a standard, let us say, plasma creation environment, the number or the average number of atoms displaced would vary, let us say, from 0.51 in the case of titanium to 2.4 in the case of gold in this list that you see here. The basic features of sputtering include, the wide choice of materials, because in the case of evaporation, if you recall, we could only have materials which have relatively low melting points. And since the sputtering is done usually at a lower rate, they have better adhesion characteristics, and there are ways in which one can engineer the sputtering to have complex stoichiometric films. The films can be deposited over a larger area by sputtering, and hence compared to evaporation, sputtering process is more popular, more widely used when one would want to recur over larger wafers, especially in industrial facilities. The deposition yield, as I mentioned, is proportional to various factors that we have seen in the previous thing. Disadvantages include the high cost of equipment, and sometimes there are substrate heating happening due to the secondary bombardment, and obviously, as I mentioned, the deposition rate is relatively slow. There are essentially two types of sputtering depending on how one creates the plasma. Can create a plasma with the DC for conducting materials such as metals. We create an RF magnetron based plasma for dielectrics or insulating materials, and that has better control, especially for depositing this dielectric materials. And once again, this is also very popular in large area films, especially for industrial applications. And there are challenges in creating uniform films, and a proper utilization of the source, which is essentially the target material for the films. In this approach, it is also possible to do a co-sputtering with multiple targets. So, when we need a composite film, it is also possible to locate these targets appropriately, so that we can have a co-sputtered film which will be based on the various materials that are provided with individual targets. So, that is one key advantage of using sputtering. If you look at a basic comparison between evaporation and sputtering techniques, the one that would stand out include the low rate of deposition of sputtering and the unlimited choice of materials that are there in sputtering. Relatively, sputtering gives better purity films and can be used for again alloy kind of materials, but obviously it is more expensive and results in films that are of typically better quality than evaporation. And we look at how various materials, or in this case metals, could be deposited. We can look at them from the point of view of their melting points under standard conditions, and as you could see, aluminum having a relatively lower melting point can be deposited using thermal evaporation techniques, and materials having higher uh, evaporation, higher melting points would require other ways of melting or sputtering kind of approaches for their deposition. What you see here is a set of deposition equipment that are available at IISc, where you can use sputtering or evaporation kind of techniques for depositing various films. Another approach for depositing even better quality films is based on laser. In this case, as in the case of sputtering that you have seen previously, instead of using an ion beam, what we use is a laser beam, and as you may know, lasers can be used to melt materials because of the high energy of the laser, and these melted material can be arranged to be transported onto the substrate, and one of the methods is essentially based on what is called pulsed lasers, and that is typically called pulse laser deposition or pulse laser ablation techniques. The material is deposited onto the substrate actually without decomposition. So, it does not basically change its properties in this method. So, once again this is also useful when complex stoichiometric properties are required for the films, and if we have a target material with the same stoichiometry, this can be transported from the target to the substrate by the laser ablation techniques. And as I mentioned, one of the common method is called PLD, and this can be used for high quality thin films of materials such as superconducting materials. And so, the main advantage in this case is that it is relatively easy to reproduce films based on this, and the films deposited by these techniques do not require post deposition annealing, which is typically required in the case of the previous techniques, that physical vapor deposition techniques that you have seen here. Obviously, the laser characteristics and some of the other environment parameters determine the deposition rate by this approach. The next deposition approach that we want to discuss is based on chemical vapor deposition. So, in this case a chemical reaction would happen which would transform the incoming gaseous molecules, and which are typically called precursors, and we make them after the reaction the precipitate of the chemical reaction would be made to stick onto the surface. So, in this case there are no real target, it is essentially the incoming is in the gaseous form, and we need to make suitable the appropriate reactions to happen, so that the films formed by either a heterogeneous or a homogeneous chemical reaction to be formed onto the surface, and various materials could be formed onto the substrate materials at a wide range of environmental conditions by the chemical deposition schemes. Films include the silicon compounds, metals, and also various other dielectric insulators. And the process parameters include the temperature, the pressure, and the flow of the gas, and the distance on within the chamber, and the direction in which these are incident onto the surface. Is essentially the mass transport of the reactants that would result in the formation of this precipitates, and these are formed usually by gaseous phase reactions from the precursors, and as I mentioned there is a mass transport from these precursors onto the growth surface, and there is some kind of a adsorption happening there, so that the films would stick to the surface. There are surface reactions and surface migration, so that the film forms continuously onto the surface, and the byproducts are desorbed out of this surface, so that a good quality film can be formed. These byproducts are taken out from the chamber. So, one typical situation in which multiple the films are formed on multiple wafers is shown here. We have to control the pressure inside the chamber, temperature, and various parameters. And there are various types of CVD based on how we enable these chemical reactions to happen. There are techniques in which we use plasma inside the chamber, and which is usually at lower temperatures. There are also methods in which lower pressures are used, and there is specialized methods using metal organic materials are used for depositing metallic films onto this. And if you see typical ranges of temperatures, the order would include PECVD, which is plasma enhanced chemical vapor deposition, which is usually done at much lower temperatures than the other methods. And as you could see, various materials could be deposited using these approaches, and are typically used when relatively better quality films are required and thinner films are required for various applications of microsystems and integrated circuits. CVD is based on chemical reactions. For example, to form silicon dioxide, one would start with silane and oxygen, and we can make the chemical reaction happen at at a LPCVD reactor at about 500 degrees centigrade for the formation of silicon dioxide. There are also other source materials that could be used for realizing silicon dioxide. Similarly, silicon nitride can also formed either by LPCVD or PECVD, and based on various other factors, and typically the temperatures are 800 degrees centigrade for LPCVD of silicon nitride. It is also possible to deposit silicon layers onto a wafer by using LPCVD. Usually LPCVD is used in this particular context, by the way, and at a pressure ranges from 0.2 to 1 torr is used for this, and the deposition rate is typically 10 nanometer per minute at about 600 degrees centigrade. But if the temperature is lower, what is formed is usually amorphous silicon. Now, the question is, what is really this polysilicon, and why is it typically used in IC fabrication and in many VLSI kind of devices. As you could see, polysilicon is essentially what is called the polycrystalline silicon. So, it is not a single crystal silicon that will be formed by this approach. If you recall, when we talked about substrate silicon wafer, it is essentially a single crystal silicon. So, from one point to another or anywhere on this wafer, the silicon atoms are at a fixed distance, which is a multiple of the lattice constant of the wafer. But in the case of polysilicon, what you will see is locally it consists of small crystallites, but there are grain boundaries, and beyond which the lattice is not continuous, and hence it is not a single crystal silicon. But it is a very good structural material for MEMS, and most of the properties of polysilicon, especially in the context of MEMS, are very similar to that of silicon, and it can be doped to various levels of conductivity, and hence it can be used as an electrode material as well, and hence it has multiple roles in many microsystems. The resistivity could be as high as about 500 micro ohm centimeter, and as I mentioned, it could be used as gate electrodes, and it is typically used in the CMOS technologies. It also can form an ohmic contact with the silicon, and hence it is widely used. It is easy to pattern to, and it is widely used as the electrode material. It is possible to deposit metallic films also by CVD techniques, and typically these are called MO-CVD, metal organic chemical vapor deposition schemes. So, what we have is that precursor material is typically metal organic of the particular metal to be deposited. This results in extremely high quality films, and and hence but at a very low rate of deposition. Hence, it is used for specialized components, for example, for optoelectronic devices, and for example, gallium arsenide or gallium nitride based devices and things like that. In a typical MO-CVD system, various reagents are injected into this chamber, and just like in any other CVD scheme, we make the chemical reaction to happen, and we also do some kind of rotations and things like that, so that a uniformity and good control of the film deposition can be obtained by this approach. As you could see from the list here, many metallic films can be formed based on their organic precursors that are used in these CVD systems. Again, one more although not very much used in the context of microsystems per se, even higher control of film characteristics can be obtained by an approach called molecular beam epitaxy, where which is also a very low deposition scheme and as you could see from here, a highly complex kind of a system is required for this purpose as well. Changing gears, one of the simplest approaches and probably the most widely known approaches is based on electroplating. I am sure you would have heard about this in various other contexts. What you would require is an electrolyte bath in which you apply a potential between the cathode and anode, and there is this deposition can be resulted in onto the wafer by a process known as electrolysis. It could be used for again for a wide range of materials, and it is the process is governed by Faraday's laws, and which essentially would convey that the magnitude of the chemical change is proportional to the current that is passed through this, and the masses of the different species deposited is based on the electricity that is provided into this scheme. Another simple scheme is based on spin casting or spin coating. This is typically used for polymeric materials including photoresist. What we have here is a wafer on a vacuum chuck which could be rotated, and what we do is we pour a few drops of the material to be deposited and then spin this at several thousand RPM under control and after holding it with the vacuum. So, when you are spinning, the droplets would be spread into a thin film based on the centrifugal force, and the surface tension and the rate of RPM are controlled basically to obtain various thickness films. And a reasonably good uniformity of thickness can be obtained at a quick rate by this approach. There could be minor variations in the thickness though, and typically used for polymeric materials such as photoresist, polyamide, and even SU8, which is incidentally a very common material, becoming a very common material in the for microsystems applications. So, let us look at some of the polymeric materials that are typically used. Photoresist is a resist material, and as you will see soon in another lecture, this is required for the pattern transfer in most instances. Polyamide and PMMA, polymethyl acrylate, are very common materials, plastic materials, polymeric materials used in various microsystems applications. As I mentioned, SU8 is fast becoming again another popular polymeric materials which can have a wide range of thicknesses. So, when you need a thick resist material for some reason, one can use SU8, and it can also be used as a structural material. It is a polymeric material, and it can, the bonding between these different polymeric chains are so strong, and hence it has a wide range of applications in microelectronics, mechanics, fluidics, and even to some extent, some kind of packaging can be done using this method. In the facility that is here, we have done a wide range of structures for microsystems using SU8 materials, and as you could see from the images here. Let us look at how one can determine the quality of the film, because that is essential in repeating, in reproducing materials and things and devices and things like that. Composition of the film is obviously important, because that determines its all the other characteristics to begin with. The grain size is also important, because that, as you have seen in the case of polysilicon, that decides the overall characteristics, including the electrical characteristics of the film material. Thickness can be controlled, but yet the thickness that can be formed, as well as the uniformity of the thickness that can be of the film that can be realized is obviously important in realizing good quality devices. In the context of deposition of films, another important parameter is the step coverage. This happens when you are depositing a film onto a geometry that is already formed, and see, for example, you have a wafer in which some kind of structure is formed, which has a step variation pre-existing. So, in this case, when we transport materials from a source onto this surface, typically a line of sight rule is valid there, and hence the vertical edges of the structure may not get coated in most of the approaches. So, there are approaches such as rotating the wafer holder, or one need to use non line of sight approaches for depositing films when a continuous coverage over stepped geometries are required. Adhesion is obviously critical in retaining structures attached onto the surface of the wafer. It is also important that the materials that we would choose are corrosion resistant, so that the performance are retained over a period of time. The film characteristics that I have mentioned are evaluated using various instruments that are shown here. The thickness as well as the uniformity of the thickness can be evaluated using a surface profiler. What you see here is a contact type surface profiler, where there is a scribe which would actually move and its position is recorded, and based on the position of the tip of the scribe, one can determine the height of the surface of the film. There are semi-optical methods in which the film thickness can be measured. There are electrical techniques in which the film conductivity and other characteristics can be evaluated. There are methods based on probe stations for measuring various other electrical characteristics. For example, the junction effect, the capacitance, and things quantities like that could be measured by using accurately positioning probes onto the devices that are formed on the wafers. Let us also look at the typical thin films that are used in the context of microsystems. As we have seen in the beginning, thermal oxide of silicon is an important component in this context. There are various dielectric materials other than silicon compounds that could be used in microsystems, and these include polymeric materials. Some of those I have already discussed. There are also several ceramic materials, and as you have seen, these could be deposited using techniques such as the RF sputtering, because these are typically non-conducting materials, and also the PLD kind of techniques. And we have seen various chemical vapor deposition schemes for the deposition of the silicon compounds. And as I mentioned, polycrystalline silicon is another important material in the context of microsystems. We also would require metallic films. Although polysilicon is conducting, in many cases that is probably not, that conductivity is probably not sufficient, and we would need to look at metallic films, and various materials including aluminum are used in this context. In the context of smart microsystems, we also come across various smart materials typically, and are also called active materials. These include ferroelectrics and piezoelectrics. These have very interesting characteristics and could be used in several sensors and actuators. Once again, these are essentially ceramic materials, and the same methods that we discussed here, which are sputtering or laser based techniques, could be used for their deposition as well. And as you have seen previously, these thin films can have multiple functions. For example, a very common example is the case of polysilicon, which could be used as a structural material and also used as the contact material. So, the roles of these thin films are multifaceted, and for various purposes these materials are used in the context of MEMS and microsystems. Now, we can also look at how these materials are chosen for various applications in microsystems. Especially in the context of microstructures, one would want to primarily look at the mechanical properties, the elasticity, the Young's modulus of the material, and as I mentioned, that depends on the material per se as well as how it is deposited. The chemical and electrochemical properties of various materials are relevant. Biocompatibility issues have to be looked at. Whether these, if you are building let us say system on chip or bioreactors, this becomes very critical. Electrical characteristics, especially for semiconducting materials, one need to look at the mobility and the doping level, which would essentially result in the conductivity. Then thermal properties such as the heat conductivity, the expansion coefficient are very critical, especially when we have multiple layers of thin films having different materials, their expansion coefficients have to be looked at very carefully, so that there is no thermal stress between the various layers of films that are formed on the surface. Another critical issue when we are selecting materials is the feasibility of various processing capabilities that are available. And how we can deposit and pattern these materials, and whether the required infrastructure are available in using them. In the optical properties are also important, because that plays a major role in determining in many of the other characteristics of the film. Commonly used metals include aluminum, gold, along with some other layer below that. There are also platinum and palladium, which are used in several contexts. There are several silicon based materials that I have talked to you about for various applications, including the insulator and as a coating, but more importantly in many cases as an etch mask. I will come back and discuss about the use of silicon nitride as an etch mask when we talk about etching of silicon wafers. Polysilicon, as I mentioned, is another important silicon based method. There are also several forms of silicon dioxide which are used in microsystems. Silicon dioxide can be used as a as a film. It can be used, it is also used as the substrate material in various contexts for microsystems. And silicon dioxide is also the constituent of glass, and various forms of glass are also used in microsystems. So, what we have seen in this lecture today is a set of schemes with which thin films could be deposited, and a list of thin film materials that could be used in microsystems. So, I hope this would be useful, and I would like to stop here, and we will discuss about various patterning techniques in subsequent lectures. Thank you.